Hello everyone. Today I'm going to explain about my design on multi-sensor interface for safety and range. Let's get into the topic. First we have to focus on the basic necessary components, uh, Raspberry Pi like that, and sensors. We are going to deep dive on those topics first, and then I am going to reveal my design basically. First, Raspberry Pi. Actually, Raspberry Pi is actually, in short, I can say it's a tiny computer uh, which can able to do make it powerful for learning programming, hardware interface, and real world problem solving. And it has a pin that is GPIO. We can say ground VCC like that. We also have the GPIO pin that is general purpose input output. The pins, these are the pin where we will connect actually the sensors like so on. So we are going to integrate two sensors. The one is ultrasonic sensor and one is TOF, time of flight sensor. Okay, and first ultrasonic sensors. Actually, an ultrasonic sensor, the name itself, it actually represents the ultrasonics. Ultrasonics is nothing but a sound wave which has more than frequency 20 kilohertz. We can able to our audible sound waves is only between 2 kilohertz to 20 kilohertz, but while in the case of ultrasonic sensor it has more than 20 kilohertz, so it's I can say the it can travel, we actually know the speed of the light, no? So we are going to analyze only the time that is taken by the obstacle and then have to reflect it back to the sensor. So this is a formula that we are using. Distance is equal to time taken into speed of sound by 2. Actually 2 is come from, we know that there will be a reflection, again the distance is coming. So we are going to find the time, uh, actually take the 2t basically, because first it's gets what can I say, it's getting passing through the obstacle and then reflecting, so it's taking 2 times of the distance x. So we are dividing by 2. That's a logic behind that. And we can say the time of flight, it actually uses a light or IR, infrared photons. So it can the advantage of TOF sensor over the ultrasonic sensor is uh, it can detect the sub millimeter changes as well. What it actually represents? It actually says that it has more resolution than ultrasonic sensor, because we know that the speed of the sound uh, is very less when compared to the speed of the light, and also the speed of the sound is the sound wavelength is more larger than the light wavelength. So we know resolution is inversely proportional to lambda, that is the wavelength. So time of flight which has a least wavelength will have a higher resolution, so it can able to detect the sub-millimeter changes as well as so finer resolution. So you can say light is millions times shorter in wavelength than sound. Let's get into next topic. Yeah, deep dive to software for fusion algorithm. So the objective of this presentation is what software we are using for this algorithm, um, uh, for detecting the precise range, even for the short range as well as for the long range. So the key idea for that, I have actually given the key idea is to use the ultrasonic sensor for fast, close safety, and time of flight sensor is for accurate longer range navigation. So this is a key idea that I am actually done. Ultrasonic sensor is for short range and TOF sensor is for the long range that I am using so far. And then we know that ultrasonic and TOF sensor both have the strength and the weakness. We know ultrasonic is good for quick safety detection but has a lesser resolution. TOF is more accurate but may struggle at very closer range or within like certain materials. So we have both cons and what say what can I say is that advantage and disadvantages. So we are doing a mixed algorithm, fusion algorithm. We are taking the both readings of ultrasonic sensor and TOF sensor, and then we are mixing those readings and the calculation we are doing and the algorithm that we are computing that, from that we are getting a realistic, what can say, error um, least error value that we are getting, and it's almost equal to accurate. So it is also going to prevent from our what can say, noise spikes, impossible reading. So if one sensor fails, or we can say give unrealistic value, the other algorithm lowers its confidence and release uh, more on the other, we can say like that. Like that we can say, um, this is a concept that I am using. In this I am using the fusion concept of weighted fusion method. So in this um, you can see read ultrasonic data, read off data, validate and filter the both, and monitor sensor is actually doing some help, doing some work, and applying the adaptive some logic like fusion logic, and output is actually a distance used for navigation and control. That is what we are doing so far. And basically we can say in this I have actually done, if we always priority safety, if either sensor detects the object below the emergency stop threshold, trigger emergency stop. If any actually I mean, if any sensor reports obstacle closer than emergency threshold, the system triggers a stop. You can say it's actually triggers actually a stop. Safety is actually very important than accuracy. So that is where the logical I have constructed in Tony IDE, that is actually Python, that is supported by uh, Raspberry Pi. Okay, and actually done some weighted resistance. If the close range is below the 50 centimeter, then the ultra and trust the ultrasonic sensors. Ultrasonic sensor will have more dominant. Their reading will be dominant than um, top sensor. For long range, you have to trust the top sensor more. Okay, and fusion algorithm. Okay, fine. Now we are going to deep dive into fusion algorithm. I have said one concept, weighted average. We have a lot of topics. We have a lot of fusion algorithm, and I'm going to explain only weighted average fusion. But still, I have noted four fusion important types: weighted average, Kalman filter fusion, complementary filter fusion, Bayesian fusion. And this is what I have done. In this you can see in my design I have to use weighted average fusion algorithm, ultrasonic distance reading, top distance reading, weighted fusion, fuse distance, and then confidence that we are getting. That's it. Confidence means accurate reading or least square error method, we can say like that. Okay, now we can say that uh, weighted average that I have actually thought about that. In Kalman is also, I can say it's a use, basically uses a mathematical model to predict the next, I think next values, and compare that value with the actual sensor value. Like we can say using the there will be some pen we can take, and we can say I have one formula for that. Actually, the formula for that I have is estimated update, or I can say it as a predicted state is equal to x bar, we can say, plus u. X bar represents the previous estimate and u represents some model based prediction, like some algorithm that we are implementing in that. So actually I'm saying that using this is actually representing the gain. We have another gain formula. I decide how much where to predict the prediction and where to trust the measurement. Okay, this is what the Kalman filter represent for us. And then complementary filter. This is used for different combina combining different sensor characteristics. Complexity is low for that. And then weighted is actually simple. It's actually uses the weighted average, but we will have each sensor reading with some certain amount of weight, by which we will get a we can say it's close to the accurate value. Okay, this is what I have done so far. And now let's get into fusion, guided fusion method. Okay, let's say this is what the connection that I am, a circuit diagram that I have made. This is a Raspberry Pi ultrasonic sensor, and this is actually top sensor. Plus 5 is connected to VCC. Likewise, the ground is connected to ground of the ultrasonic sensor, and GPIO 223 is actually connected to trig pin. Actually, trig pin, trigger pin. Actually, it's actually output pin of ultrasonic sensor, and GPIO 24 is actually uh, connected with echo. That is actually input for the ultrasonic sensor. And this is what I have done. Likewise, this is also done for TOF, SDA, SCL. Okay, this is what I have done. And here you can see there is two resistors that I am using. So this is I have actually used nothing for, it's actually used for voltage divider, because we know echo pin cannot able to accept 5 volt, because ultrasonic equipment output going to be 5 volt. So raspberry can accept only something, I can say about like 3.3 kilovolt. So that's why we are doing the resistance method, so that we are doing a voltage divider concept, due to which our voltage will be dropped and will be split across in, based on the series network of say, resistor connection. Okay, so this resistor actually protect Pi from Raspberry Pi from damage. Okay, this is what the concept that I am using, and here you can see the SDA of I2C. I2C means integrated circuit, I think so. Yeah, and SCL is DA. SDA means series data. SC means series clock line. This is two line that inter. I2C is actually one of the communication logic from where I can say a communication protocol that are a microcontroller, or like Raspberry Pi Arduino, to communicate with sensor using only the two types of wires. That is, we can say I have actually said series data and series clock. Okay, and can connect many sensors at once, I can say. And here we have two. It's actually digital concept. So master and slave will be actually on the topic of digital. So master is actually the concept for it is a master as a Raspberry Pi, slave as a sensor. Master actually always as a word represent understand by the word, we can say that controls communication starts, and we can say it's uh, stops it, can able to control the slave, I can say sensor. The sensor actually as a slave responds when asked provided data like distance, we can say. Okay, and this top sensor will give a digital distance value, not anything pulse to bit, like that I'm saying. Okay, let's get into the topic. Here you can see the distance. If distance is less than 50 centimeter, then we are giving a more weightage to the ultrasonic than this, because it's a short range. So to prevention of what can I say, noises and spikes, we are doing ultrasonic. And here you can see zero point 0.8 for ultrasonic plus zero point 0.2 for TOF, by which if you add both you will get a 1. This is what the weighted. If you have two weight, then sum of the two weights is equal, always equal to 1. That's the concept. Okay, let's get into the program that I have done. I didn't do any I didn't do uh, real hardware simulation, because we cannot able to integrate both um, TOF sensor and ultrasonic sensor in any of the online simulator as well. So I don't even have the Raspberry Pi hardware, so any hardware material I don't have. Due to insufficient process, I have just do the logic construction used have done in Tawny IDE. So in this, I have done a logic construction, how it actually works. It's actually taken the random value, and then how the weight and how the concept that I am using. It's not a real simulation that I am saying. Okay, so in Tawny IDE, I have run this code. This is actually the code for that. Here I have given a set of commands that I have given for this. Here you can verify that. Um, Here you can actually verify here random. Actually, I've given a random concepts rand. What is rand? It specify what it is actually random. So it's used to we can say it's generate a fake stimulated sensor reading. So time dot sleep. Here you can see the time dot sleep, which actually add delay between every set of cycle, because while is actually true, it will runs this code, this set of block for infinite amount of times. That's what I have done. So it's always true. It's going to be always stimulate. It always excludes a set of statement between enclosures within the while true. Okay. So in this I have actually instructed with class. You can see about that. And sorry for the inconvenience in this. um, have misplaced that class module, that screenshot basically. I will explain that. So I actually declare a class above this set of code, in which I actually declare the class sensor data. It's actually named sensor data, I think, and it defines a simple data structure. I can say it like it will actually store the data distance reading, and init, that is actually it runs whenever object is instance is created. Self dot distance, we can say, that is actually stores the distance value uh, inside the object. This is actually done. I have done, and also I have done a function, declare a function which receive the list of readings I've written, and then here you can see the averages that I have done. Okay, here actually I take three readings, and if I do from each sensor, add them and divided by its count. So it will do a what can you say, smooth reading. So it will actually do what is that, prevent from noises, because we are doing average. So it will reduce the concentration of noises, we can say. And and we are doing a weight selection. If the average, we can say, if the object is very less than 50 centimeter, ultrasonic will be more dominant. Okay, then we are giving a more weightage to ultrasonic and than top weight. So if not mean else block will be executed. So it will more than 50 centimeter. So ultrasonic weight will have less weight, and top weight will have more weight, by which we can able to do which will have more predominant for short range as well as for long range. Okay, and here we have done what is, you can see, again have done what have done if elif else if control statements. Again I'm saying that it is less than 20 centimeter emergency stop, if 20 to 50 caution, 50 centimeter means safe. Like I'm saying, it actually mimics some what can I say, robotic obstacle avoidance. Okay, and I have already said while will always have a true, so it will run set of block immediate in infinite times. So in this you can see that as data sensor data random dot uniform 15, like we can say 100 for I in range, you can say 3. Likewise I can say for top data as well. This is actually the thing that creating a ultrasonic random values, fake values and fake top values. Actually it represents some value, your random values, by which we are doing a simulations. Okay, and actually we are determining the safety status. We are status is equal to we are getting get state of fuse distance, what distance we are getting, like print, we are doing a print, and we can able to see the raw data averages and their results, fused results basically, and confidence score, and also the safety decisions that we are having. And also I have to say one thing, fused distance, actually here you can see fused distance is actually equal to average of ultrasonic average star, you can say it's actually multiplication, respective weight of W1, I can say, plus top average star W2, that is top weight. That this is actually the fuse distance that we finally will get, and this is the confidence, nothing but divided by 2. The mean of that will give you confidence, which actually score between 0 to 1. It's like a probability, I can say. Like Bayesian fusion is all about probability based. Likewise, this is not probability based. I'm saying like probability, it is taking only the value from 0 to 1 for the concept of confidence. And this is the output that I get, a random value output for ultrasonic average, top average, and we will get a fuse distance as well as their confidence, by which we understand the safe, which is the path clear. In this you can see fuse distance is this less than 50, so it's giving a warning that um, um, object is pretty close. Here it is not, like it's more than 50, so it's safe. We are saying path clear. That's it. This is what I have done a design based on a very basic concept related with the Tony Python programming, um, by which I have I have explained only the algorithm, which is weighted average fusion algorithm. And thank you.